Good day everyone. So today I am going to discuss about some topics of calculus. So are you now ready to listen? Okay, so let's start. We have now examined functions of more than one variable and seen how to graph them. Okay, so in this section, we see how to take the limit of a function of more than one variable and what it means for a function of more than one variable to be continuous at the point in its domain. It turns out out of these concepts have aspects that just don't occur with functions of one variable, since we are taking the limit of a function of two variables that the point A and B is in R squared, and it is possible to approach this point from an infinite number of directions. Now and then, when calculating a limit, the answer changes depending on the way taken toward A and B. Okay, so if usually the case, at that point, the limit comes up short to exist. So in other words, the limit must be one of a kind regardless of way taken. Okay, so let's go to continuity. Continuity is another far-reaching concept in calculus. It is a function can be either continuous or discontinuous. So one simple way to test for the continuity of a work is to see whether the chart of a work can be followed with a right without lifting the right from the paper. So for the math that we are doing in pre-calculus and calculus, a conceptual definition of progression like this one is likely adequate, but for higher math, a more specialized definition is required, utilizing limits that will learn the stand better, a much better, a higher, a stronger, an improved, a stronger, and a distant, more exact way of characterizing coherence as well. So, with an understanding of the concepts of limits and progression, you are prepared for calculus. In continuity, we characterize the progression of a function of one variable and saw how it depended on the limit of a function of one variable. So in specific, three conditions are necessary for f of x to be continuous at points. So there are three essential types of discontinuities: the removable or the point, the discontinuity, the chart features a gap at a single x value. So next is the infinite brokenness. The work goes toward positive or negative limitlessness. Okay, so imagine a street getting closer and closer to a waterway with no bridge to other side. Okay, so next is the jump brokenness. The graph hops from one foot to another. So envision a superhero going for a walk. He comes to a dead conclusion, and since he can fly to another street, we gonna recall for a limit to exist. So the left and right limits must exist. So it be finite and be equal. So infinite discontinuities have infinite left and right limits. So jump discontinuities have finite left and right limits that are not equal. Infinity, along with its symbol infinity, is not a number and it is not a place. When we say in calculus that the function becomes infinite, we simply mean that there is no limit to its values. So let f of x, for example, be fraction. Then as the values of x become smaller and smaller, the values of f of x become larger and larger. So no matter what large number we name, it will be possible to name a value of x such that the value of f of x will be larger than that number we named. Okay, so when we say that the values of f of x become infinite or tend to infinity, we say that as x approaches 0, the limit of f of x is infinity. Now, a limit is a number, a boundary. So when we say that the limit is infinity, we mean that there is no number that we can name. Okay? So when the variable is x and takes on only positive values, then x becomes positively infinite. Okay, so if x takes on only negative values, it becomes negatively infinite. Okay, so in both cases, we mean that no matter what large number that we name, we get to a point in a sequence of values of x that their absolute values become greater than m. Okay, so when the variable is a function of f of x and it becomes positively or negatively infinite when x approaches the value c, although we write the symbol limits for limit, lim for limit rather, those algebraic statements mean that the limits of f of x as x approaches c does not exist. Again, a limit is a number. As for the symbol infinity, we employ it in algebraic statements to signify that the definition of becomes infinite has been satisfied. That symbol by itself has no meaning. Okay? Calculus is applied to things that do not change at constant rate. Okay, so velocity due to gravity, births and deaths in a population, units of y for each unit of x. The values of the function called the derivative will be that varying rate of change. Now, since we considered x to be the independent variable and y the dependent, then any change delta x in the value of x will result in a change of delta y in the value of y. So, in a straight line, the rate of change, so many units of y for each unit of x is constant and it is called the slope of the line. Okay? A tangent is a straight line that just touches a curve and a secant is a straight line that cuts a curve. So, we cannot, however, evaluate deltas exactly at p because delta y and delta x would then both be zero and that the value of deltas would be completely ambiguous. Okay, so therefore we will consider shorter and shorter distances with delta x, which will result in a sequence of seconds and a sequence of slopes. So, and we will gonna define the tangent at p to be the limit of that sequence of slopes. So that slope, that limit, that will gonna be the value of what will be the derivative, since the differential calculus is the study of derivatives, diba? So it is a fundamentally concerned with functions that are differentiable at all values of their domains. So such functions are called differentiable functions. Rate of change, it is the rate of change function is defined as the rate at which one quantity is changing with respect to another quantity. So in simple terms, in the rate of change, the amount of change in one item is divided by the corresponding amount of change in other. Okay, so the rate of change tells us how something changes over time. Okay, so the distance traveled by a car in a certain amount of time, and then work done per unit time, and then work done and the number of people required for doing it. Okay, so we will gonna use the rate of change formula. So here is the first. Rate of change is equal to change in quantity, which is 1 divided by change in quantity 2. So another is rate of change is equal to change in assignments done over the change in hours. Okay. The polar coordinate system is the line segment starting from the center of the graph going to the right is called the positive x-axis in the Cartesian system. So it is the polar axis. So the center point is the pole or origin of the coordinate system and corresponds to r is equal to 0. So coordinate systems are really nothing more than a way to define a point in space. So for instance, in the Cartesian coordinate system, at point is given the coordinates x and y, and we use this to define the point by starting at the origin and then moving x units horizontally followed by y units vertically. So this is not, however, the only way to define a point in two-dimensional space. So instead of moving vertically and horizontally from the origin to get to the point, we could instead go straight out of the origin until we hit the point and then determine the angle of this line that makes with the positive x-axis. Okay, so we could then use the distance of the point from the origin and then the amount that we needed to rotate from the positive x-axis as the coordinates of the point. in calculus, sometimes functions behave differently depending on what side of the function that they are on. So a one-sided limit is the behavior on one as it were one side of the value where the work is undefined. So in case the two one-sided limits are not break-even with, the two-sided restraint does not exist. So if f of x is close to some negative number and g of x is close to 0 and negative, then the limit will be infinite. So one can also have one-sided infinite limits or infinite limits at infinity. We presented the concept of a limit gently, so approximating their values graphically and numerically. So following came the thorough definition of the limit alongside an, as a matter of fact, repetitive strategy for assessing them. The previous section gave us tools which we call the hypotheses that permit us to compute limits with more prominent ease. So, chief among the camps about where the reality is that polynomials and level-headed, trigonometric, exponential, and logarithmic capacities and their entire trees, items, or etc. all carry on nicely. So, in this area, we thoroughly characterize what we cruel by nicely. So, the phrase if and only if means the two statements are equivalent. They are either both true or both false. So, if the limit equals L, then the left and right hand limits both equal L. So if the limit is not equal to L, then at least one of the left and right hand limits is not equal to L. So it may not even exist. Also, note that as with the normal limit or the limits from the previous section, we still need the function to settle down to a single number in order for the limit to exist. So the only difference this time is that the function only needs to settle down to a single number on either the right side of the x is equal to a or the left side of the x is equal to a, depending on the one-sided limit that we're dealing with. Okay? So when we're looking at limits, it's now important to pay very close attention to see whether we are doing a normal limit or one of the one-sided limits. Okay, so let's now take a look at to the sum of the problems from the last section and look at one-sided limits, okay, instead of the normal limit. So this should make some sense. So if the normal limit did exist, then by the fact that the two one-sided limits would have to exist and have the same value by the above fact. So if the two one-sided limits have different values or don't even exist, then the normal limit simply can't exist. Okay, so hopefully over the last couple of sections, you've gotten an idea on how limits work and what they can tell us about functions. So some of these ideas will be important in later sections, so it's important that you have a good grasp on them. Okay, let's move on to the derivatives. So the essence of calculus is the derivative. So the derivative is the instantaneous rate of change of a function with respect to one of its variables. So it represents the slope that they can be used to find maxima and minima of functions. So as we move forward, I will going to give short overview about maxima and minima. So but first, let's explore more about derivatives. Okay, so derivative of a function using definition. To use the definition to find the derivatives of any functions, we just need to remember its formula. So when we solve some functions using the definition of the derivative, we just need to plug in the functions sa atong formula. Okay? So in solving derivatives, there are lots of formulas that are, of course, very essential in getting the answer. So from the basic differential to trigonometric function to quotient product, power and chain rule, and the laws of logarithm, product rule. Okay, so let's go first to the product rule. So the derivative of the product of the functions is the first function times the derivative of the second function plus the derivative function times the derivative of the first function. To make it even more simple, there is kaning formula na to nga gigamit, okay? So let's go to power rule. The power rule is used to find the slope of polynomial functions and any other function that contains an exponent with a real number. So in other words, it helps to take the derivative of a variable raised to a power or the exponent. So all we have to do is first, we're gonna move the exponent down in front of the variable. Second, multiply it by the coefficient. And the third is decrease the exponent by 1. So that is. So let's go to chain rule, where there are problems required to use of the chain rule. So the chain rule is a rule for differentiating compositions of functions. So we involve an intuitive approach. Okay, so higher order derivatives, finding a second, third, fourth, or higher derivative. So it is not so simple for no voice or beginners like me. Ang ako lang na subtendry is to get the second derivative of a function is just the derivative of its first derivative, and then the third derivative is the derivative of the second derivative, and the fourth derivative is the derivative of the third, and so on. So for example, here's a function and its first, second, third, and subsequent derivatives. Okay, so implicit differentiation, this is the technique of implicit differentiation that allows us to find the derivative of y in respect to x without having to solve so the given equation for y. So next is finding the maxima and minima using derivatives. Okay, so a maximum is a high point and a minimum is a low point. So maxima and minima in calculus are found by using the concept of derivatives. Okay, so we say that if function of f of x has a relative maximum value at x is equal to a, if f of x is greater than any value immediately, so preceding or following, we call it a relative maximum because other values of the function may in fact be greater. So we say that the function of f of x has a relative minimum value at x is equal to b if f of b is less than any value immediately preceding or following. So again, other values of the function may in fact be less. So with that understanding, then we will drop the term relative. So the value of the function, the value of y at either a maximum or a minimum is called, okay? So thank you so much for listening, and I hope that you've learned something from my discussion a while ago. So God bless us all and have a nice day.